Hey everyone, this is Dave. It's not Prabjhot. Unfortunately, the lecture recording for number 10 didn't work. It was the October 3rd lecture, even though it says the 2nd on this slide. And we're just going to redo basically what Prabjhot did in class, so you have the audio over these slides. Okay, so the point is pointers in C. We've reviewed that a little bit in lecture 9 and before, only working with C strings. And now the point is to tell you essentially everything you need to know for 206 about single pointers and how they work with other kinds of variables other than C strings. Okay. The recap is that C strings are, we said, arrays of character variables, but their equivalent representation is that they can be represented as a pointer. So when they're represented as a pointer, then we can think of this hello world as being this box in memory. My drawing is terrible. Right? We have all these different characters, and then we have this pointer myString who holds the address to the first character in the string. So that lets you do things like printing myString, and it also lets you do things more flexibly than the array did. If you remember from lecture 9, myString is allowed to be plus plus, and then we'd point at the E, right? If we did plus plus, and it's allowed to do things like plus 5 or so, and that could point here. So pointers let us move around in strings. They held an address. Whenever we did these operations on them, they would represent an address of a different part in the memory. But the way that they got their addresses was a little bit magic, and it maybe so far seems like they're only useful for C strings, and absolutely not. They're useful for all other kinds of variables. So if we look at another kind of variable like an integer, then it's not super obvious when you just write int I, but if you think it through, that's supposed to be a variable which will hold one integer value, and computers can only represent integer values with ones and zeros in the memory, so it has to reserve memory for the variable. Whether you want to think about it or not, in 206 you have to think about it. So there's this box, it's enough memory, 4 bytes for one integer variable I. So far it has no value. Once you say int I equals 3, right, the value inside that memory is the binary representation of 3, right, something like a 1 and a 1 in the two least significant bits. Then we can think about where is this memory, where is this little box in the overall memory, and we use addresses to keep track of where things are in memory. And so we can start writing below our variables address. Okay, so this is this is the address of I, right? That number right there. It doesn't mean that the value of I is 214. We can still say int I equals 3. The 3 will be inside the the bits of the memory, but there'll be some additional thing like your street number. It says how do I get at that memory, right? And when we're just saying int I equals 3, we don't have to think about the address, but once we start wanting to use pointers, they let us think about the address, right? If that's what we want to do, and that's what we want to do a lot of times in C and systems programming. So how can we actually get the address of I? That would be by preceding the variable identifier, the name, so I, here with the ampersand. Okay, so the and or ampersand sign, it says address of. Okay, so this thing here, I said address of I over there, and this is also the symbol in C, address of I. Okay, would be there, and I is how you represent the value 3. Address of I is how you represent the address 214747 and so on. Okay, so both those things exist. They exist whether you want them to or not. Sometimes GCC just deals with it for you. Now the ampersand lets you think about using pointers to these kind of local integer variables. Okay, that's the use of the address of operator. Okay, and we'll see here that you can do different kind of operations with them. Int I equals 3, and now you can print both the value. So when we use %d, that means we're trying to print an integer here, and so this will print 3. And then we can also say what is the address used to store that memory, and we use, like I showed, ampersand So address of I, and we have a new printf code, %p. That means print a pointer variable. It's just sort of shorthand for the data type that's used to store addresses. On most computers we're going to deal with, that's a long int. So it's like a 8-byte integer, 64 bits. You can also use LD and it will print almost the same thing. But it's nice when you're actually printing addresses, use %p because it perfectly fit always to the type which is used to print, to store the address. Okay, so it's just a number. If you think of our addresses, right? 3480 University Street. I mean, when I say address, doesn't mean that. It just computers use simpler things. Only a single integer number to represent every byte in the memory, right? So it's just an integer, long integer, because there's a lot of memory, right? So we can look at sort of our whole picture here. Int I equals 3, right? The value 3, the address is this longer integer number, okay? And those things would print 3 and 2147 and so on as the two values that would end up printing on the terminal. You could try this kind of code for yourself. It's a good idea to put this in a main function, run it, make sure you believe you get the same answer, right? And then that's just the beginning, so it's not very interesting or useful yet. But now the question is, what will we actually want to do with this address? And of course, we'll be starting to use it with pointers. Okay, so that's coming. Okay, so the pointers that we talked about before, which we're indexing to C strings, I already said that they hold the address. And so I said, that the C string has memory and there were addresses to point to different characters within the C string. Well, it's exactly the same concept. So every pointer holds an address, and the pointers we'll be using today will just hold the address of single variables. There's nothing different about the address of single variables or C strings. We just use a little bit different syntax to access them. Okay, so, and a pointer, when referring to normal variables, will allow you to access the variable. That means use its value and change its value without using its name. So this can allow you to write more reusable code, which we'll get to see a little bit by the end of this lecture. Okay, and if we want to draw out our pointer, it also holds a box, right? It's also holds an integer value inside, and it also has another address because it's space in memory all on its own. What's inside the pointer's value is an address, not sort of an underlying value that you're using in the code. So not like 3, but like another address, right? And this one, we'll hope, we don't know what this value is yet because we haven't initialized it. But a lot of times compilers are nice to you, and maybe this equals 0, which also is the special word null. And so if you're lucky, you'd like a pointer which is uninitialized to equal null. And if you don't believe in luck and you want to be a good programmer, then this should always look like this. So if you set a pointer equal to null, when you initialize it, then you're essentially keeping track of saying, I haven't put a real address there yet. I don't know if this is A or B or a string or whatever else. And so null just means not using it yet. I don't have an address. It's a unique sort of aspect of pointers. Although it's similar to just an int variable before you assign a value, it's not safe to use the value, right? So similar with pointers, but worse things might happen if you try and use the pointer's value too early. Okay, so that's a pointer. The difference in declaration, right, is that we have the star after the type and before the variable name. It can either be where it is here. It can also be right after int. Okay, only one of them, right? So we can write the ones that's there. And actually there can be also spaces in between, and that's fine. But any time there's a star in between int and the variable name, we'll read that out int pointer. And we'll distinguish that star, which we'll note that this is when we declare the variable. So it has a very special meaning. We think when we declare a variable, we give it a type. So the star we're using here is the type of the variable. It's not operating yet on the variable itself. It's not like we multiply by p or we dereference, which is the operator we'll see star has with pointers later on. But so that we just read, I want a new variable. Its type is int pointer. Okay, that's what we read. Okay, and of course, we're not going to leave that null in our pointer's value because otherwise it would be useless. And so what we want to do with our pointers is we want to create an integer variable, give it the value 3, and then we want to point our pointer at the variable, in this case I, by assigning the address of I. Okay, address of I, that's ampersand I. We want to assign our pointer the address of I, so that means copy the address value, right? When we did address of, we got this value, and copy it. Every time you say equals, one variable equals another variable, you always take the the right-hand side value and you store it in the left-hand side thing, right? What can pointers store? Addresses. Okay, so notice that the integer i's address is different than the pointer's address, but they kind of use a similar, they're close by, which might mean they're both in the same program. They're within our program's memory, so they're both parts of our a.out, let's say, and right, but they don't hold exactly the same value, and precisely now p points at I because it holds its address, right? If we also had a j, and we said, now p equals address of j, we would change the value inside that the pointer is storing. We're about to see that in a little bit. But for now, this is the simplest way you point a pointer at a variable. Okay, so nothing too complicated there. And you can also print out these different values if you printf now p without doing star p, but if you just did printf with %p, and then that's the way you print out pointer value, and then you put p afterwards, you would get in this, if it was these values, you get 0012 FED4, right? So that's, you'll get its value that it's storing. Okay, and that looks like this. So we hope that if all goes well and this is the setup, then you're going to see this outputs 3. This outputs, I'll shorten the writing, so you don't have to read my chicken scratching so much, right? So that outputs the address of I, which is FED4, and when we say also P, that's also FED4, right? Later on, we're going to see, okay, what would happen if you said address of P, and that would end up giving you E4. And that could also be done with the %p code, but that's a little bit beyond. That's not going to be on the midterm yet. That is going to be something called the double pointer. It's coming. That's a preview. But for now, I'll erase that so it doesn't confuse anybody. The things that are on this slide, you should know what to expect here. And if we gave you the diagram on the bottom and the printf values, you should be able to tell what prints on every line, right? Okay, so far we could point pointers at integers, but they don't have any effect. They don't change what's happening in our program up to this point, and so we need to actually use the pointer to change some values in memory of other variables, and that's the main job of a pointer. And the main tool to do that with normal variables, not in our C strings, where we were doing a lot of indexing, is something called the dereference operator. And so here's where, on this slide, we have to start being very careful about what the asterisks, the stars, mean in our C code. Okay, that's why I was highlighting it before. So in the first 2 lines of the example, that's exactly what we've seen. A new integer variable, it holds a value 3, is on line 1. Now a new pointer to integer named p, and it holds the address of I. And so this ampersand says it's part of the type, and this says new variable, which is a pointer to an integer. Okay, and then we're starting to printf. We printf the value at I, which we were doing before, but now we print the value at I equals again with %d. So we're printing just an integer, not address value. And here we're using this new operator, which we haven't talked about in this set of slides yet, called value at address, or called indirection operator, or called dereference operator. So just many names for the same thing. I like to say now you basically follow the pointer and you grab the value, right? So value at the address that was being stored. I like to think about the arrow notation. So P is pointing at I, and you follow the arrow where it's pointing, and you grab the value of I. Okay, so that's why you can do %d, and this is going to print now 3 and 3. Okay? And again, hopefully on the midterm and stuff like that, you could understand that. And it's not just printing. We can use now star p in any other place in our program. Okay, so int b equals star p, right? We can make another integer also equal 3 by pulling this up. We can do star p plus 5. Okay, that's 3 inside star p plus 5. This equals 8 if you store it somewhere else in the program. We can do star p plus plus. I'm using these brackets because we have to distinguish the math being done on the integer after star grabs us the integer value, versus if I didn't have the brackets, then it would mean moving the pointer around in memory, right, and then dereferencing the result. Okay, so we have to keep those things separate, but here we're just thinking about the fact that we can use a pointer to give us the integer value, and then we can do all kind of integer math with that value. Right, so this is where pointers will get useful. We'll be able to create pointers to our integer values, move the pointers around between the different values, and then use star on the pointer afterwards to change the value, add to it, multiply them together, all kinds of the different math operations we want to do in our program. Okay, so here we really have the level of indirection. That means we don't need to use the name I directly, but now we can use p, and p is sort of a proxy for I as long as we've pointed p at I, right? So it's an indirect way of doing computation. That's what pointers' jobs are. Okay, so some more examples of what we can print. This is where we did address of I. We did p. P is holding the address of I. So these are again the same example we had before. It's going to be 3. Address of I here is D4, the shortened version, right? I'm cutting off 0012 FE on both addresses. The address of I again we can use just P because that's what's stored inside the value of P. That's the address of I, right? You can also write it symbolically like that. So that'll also be D4, and address of P we're getting E4. Address always the number below the box where you say that's how I know where in memory it's stored, and the stuff inside the box means the value. That's what's stored inside those spots. Okay, and you can notice that the star p is saying follow the arrow, follow the address to where that memory is stored, and grab me back. Right, star p says follow the arrow and grab me back the value 3. Okay, so we can start building up more interesting examples now. Here we have 2 integers, I and j. They're on the right-hand side. They're at different memory locations, so they have different addresses. And now we're going to make 3 pointers. We're initially going to point p at address of I. So, if we were going to write inside here, we would write D4. That's holding that address, and that's why we can draw the arrow. The other ones have no arrows drawn, right? So again, they may be pointing to somewhere random. We hope, and if we were good, we might have initialized them to null. We kind of hope they might be pointing at 0 right now, which is null, right? But we don't assume anything, so if we initialize pointers like this, we just can't use them yet. So we're not allowed to yet say star Q or star R on this line down below, or we're risking a segmentation fault, right? So this is bad right now, right? So again, I'll erase it. But okay, so we're not supposed to use it right away. Instead, we're supposed to now assign them to some other addresses, right? So that's what comes next. We could do things like R equals the address of J. J is a normal integer, and so its address is this one here, right? So we can say now R is going to hold an address. That's pointer's job. They always hold addresses. R holds E0. We get to draw the arrow. It's not pointing somewhere random anymore. It's pointing at J. Okay, so now star R would return the value 5 currently. Okay, and Q at the moment still pointing nowhere. Okay, another way that you can give pointers an address is you can use the address that another pointer is holding. Okay, so right now P is holding D4. Okay, and that's why it has the arrow to I. And once we run the line Q equals P, well, that's now not star on either one of them. So that's not following the arrows. It's just dealing with the value in the pointers themselves, and values in pointer is the address, right? So so P holds D4, and here we say Q equals P. Remember what's on the right-hand side. Well, we're not grabbing the value, we're just returning the address. And so now we assign that to the left-hand side thing, that's Q, so Q now holds D4. Here R still holds E0. Okay, so now Q and P both get to be pointing at I, and either one of them can be used to change I. If either one of them is used to change I, then both the value of I would be changed, and the value of star Q and star P would be changed. They're all pointing to the same memory, so you're not allowed to change the value inside that memory independently. It's not like you have multiple copies of it. There's still just one spot to hold an actual integer value. Okay? Now, that's where some of the trickiness of pointers will come up. Okay? And over here, we can do star P equals star R, right? So star R says, follow my arrow, right? Star R, and we get the value 5, right? So when we follow the arrow, pull out the integer value, so that's equivalent sort of to writing 5 here, just the way we've set the pointers up currently. And then star P, now it says, follow my arrow, and since I'm a left-hand side, it means I'm going to assign something into that spot. So I follow the arrow, I get the memory that's in that location, and the 5 gets written into that spot. Okay, so now I has the value 5, star Q would have the value 5, star P has the value 5, and star R and J, everything. The only integer value we have here anymore is 5, right? We have lots of different address values. Nothing's changed about the fact that it's still D4. It's still D4. The pointers are still holding these different addresses. So star P doesn't change the address held inside P itself. It instead changes the value at the address, right? So again, follow the arrow, go grab its value, or go change its value. That's both of the things that the dereference operator or indirection operator can do. Okay, only sort of one more concept that we have to get ourselves through here, and that's the void pointer. So we've been dealing with int pointers that point at ints, and life is kind of easy and clear. And so a void pointer is just essentially someone that can match anything. Think of it as kind of a wild card for types. Okay, so a void pointer is allowed to point at any type. Okay, so here, P equals address of I. Well, P had type void pointer. It wasn't an int pointer, where I is an int. Okay, so you might say, okay, but wait, void doesn't equal int, but void equals everything, right? So it's allowed to point at any kind of memory. So this line is A-okay, no compile error. However, what you're not allowed to do is you're never allowed to dereference a null pointer and use it because its name is void. So even though there's int memory there, C won't let you use sort of star P all on its own. Right, so if after this line you said, just star P, and you want to printf it, or you want to add to it, or something like that, this is no good, okay? But instead, what is good is that you first cast the pointer, the void pointer, to another type. So in C, these brackets and then variable is called a cast, and that means instead of treating it as a void pointer, I want to use the type that's inside here. In this case, the type is int star. So now it says treat the void pointer as if it was an int pointer, and then do something else with it. And here we're doing the dereference operator. Okay, so this one follows the address that's in P, which happens to be the address of I still, and it says treat the memory at that spot as if it was an integer. Okay, and we know how to dereference that, so this is all good, right? So this line actually works. Okay, if we had left out the casting, it wouldn't work. Okay, and likewise, because we're having a void pointer, the value of a void pointer is it can be reused even across multiple types. Okay, so now we can do P equals address of J. It's now, wait a minute, you might say we cast P to be an int pointer. No, it's not permanent, and it doesn't stick around. It's only cast on this one line to access the value a single time, okay, on the line above. So, but P is always a void pointer type, and that means we always need to cast it to something else every time we use it, and the casting is a non-permanent operation, right? It's only that little in-place cast. Okay, so so P equals address J is okay, and now P holds the address of this floating point memory, which has inside it 3.14. And again, though, if before we can actually use star P, star P is still not okay on its own. Nothing changed there either. But because now we're holding float memory, instead we want to cast P to a float pointer, and we want to apply the star operator in it. And so, the second printf says the value of I, which is a typo. It should say the value of J, because we're pointing at J. So it says the value of J equals 3.14 will get printed out. Okay, so the good thing to practice, notably you can actually cast these pointers to the wrong type. For example, you can cast to an in pointer later on, and then you'll reinterpret the memory in a weird way, and you'll get odd results. Okay, so it's one of these things where C will let you do it. It will compile, it will run, and you'll say, what the heck, my 3.14 is outputting as, 9 million or some just random value. Okay, it's another place where C is not safe. It's up to the programmer to remember which type of memory you pointed your pointer at if you used a void pointer, and cast it to that right type of memory. So if you point at a float, cast it to a float. If you point at an int, cast it to an int, right? And just keep track. So that's not that hard. You might make a mistake, then you'll see it, you'll fix it, and no problem. But it's something C will let you do, right? We'll do that a little bit later in the class. We'll have some fun with mixing and matching types. Okay, and the special value, sort of one last concept here. The null pointer, I've already introduced it by my annotations. Null basically equals the value 0, which is an address that you're never allowed to use, and it's a good idea to do what's done on this slide. If you make a pointer, set its value, its address equal to null initially, it means I'm not allowed to use it, and that's a thing which you can check throughout your program, saying if P not equals null, then I'm allowed to print the value. But so for example, this code will never print something. It will avoid making the segmentation fault by dereferencing a pointer which doesn't have a proper value yet. Okay, so this is good programming practice, and often you'll even see the equals null written right on this line up here, int star P equals null, all in one line, because you really don't want to forget saying this equals null, so that you can always check the safety of the pointer later on. Okay, so one application of pointers in sort of a little bit bigger C program to end the lecture, we'll revisit a concept, which was the fact that C functions use pass by value. And so if you try to do a swap function where you have I and J in main, right, you set them up to 1 and 2, then you print them out, you get 1 and 2, then you call swap with 1 and 2, right, so A equals 1, B equals 2. We passed by value, so we copied the 1 and 2 into A, but A and B are, after they get their values, totally unrelated to I and J. They only copy the same values at the beginning, but as you change A and B, you're not changing I and J. That's a super important thing to remember for the midterm. Definitely going to test that kind of concept. So swap does, reverse, temp equals 1, then A ends up equaling 2, and then B ends up equaling 1. So at the end, you've basically swapped these, and so A and B are swapped, but outside here, no change on I and J, right? So if you say that I and J change, you're losing marks on the midterm. C is always passed by value no matter what you do. So this outputs 1 and 2, this outputs 1 and 2. Okay, so this swap is broken. It's not a good way to implement swap in C. And luckily, we made it to the point where we have pointers, and we're confident in using them. And so maybe you could pause the video at this moment and think for yourself. Do you know enough to think about how this might work? And if you have some guess or something, you can check it against what I say next. And or if you just want me to show you, here's the swap which works in C. Now, the question we want to ask ourselves is, why does this work? So here we'll draw out what kind of variables we have in swap. We have two int pointers, okay? So we have int star A remember it has a box, it can store some kind of a value. Let's say, for this sake, that the address of I is over here, and we have I, and again I'll write below, okay, it holds 1 as a value, and let's say it had that D4 address, right? And then J has holding 2, and it has something like E4, okay? And so now when we call swap, we're calling it with the address of I and the address of J. So we're going to call, we're going to say A, equals, in this case, D4, right? It's going to hold an address. Let's put D4 here, and points at I, and int star B holds B's address, J's address, I'm sorry, misspoke, E4, right? And it points at J. And then this code here swaps the values at the addresses. So everywhere that we use A or B, we use star, right? So star A says follow my arrow, and star A is 1, so temp equals 1. And then when we do star A equals star B, we say follow A's arrow. We're going to be thinking about changing the memory at I. And we say, and on the right hand side we say follow B's arrow. That means we're going to be grabbing the value at J. Value at J was 2. So star A equals star B. That actually changes the contents of A, right? And that the contents of the memory pointed to by A, which happens to be I, and that actually puts a 2 outside. Okay, and then star B, again, it says follow E4. Think about changing the memory at E4. Set it equal to the value of temp. Temp is holding 1, which we looked up earlier. Okay, and we put a 1 there. Okay, so now I and J have changed. This doesn't mean that C did pass by reference on its own. We accomplished something like pass by reference by passing values. The values were the addresses in this case, right? D4 and E4. So we still passed values. And when, let's say that we pointed A somewhere else, let's say that we happen to say A equals, the address of temp, that would not change the address of I. That would have no effect on I, so that wouldn't have been the way to code swap. But since we've been given these values, the values are addresses, we have the star operator in C, we're allowed to sort of get one step beyond. We have achieved one more level of indirection. So even though C gives us pass by value, now we can implement things which look like pass by reference. You have to use pointers. So that's why you'll see several C functions like scanf takes the address of a value, or takes a pointer to the variable, and that's so that it can change it. If you remember, scanf is a way to read from standard input and fill in values, and you can only change the values of the variables in, let's say, main, if main is passing addresses to its values. Okay, that would be something to go look up. If you never saw scanf, it's a good thing to know for the midterm. We didn't cover it super carefully, but it was sort of listed on the standard stdio.h slide, so it's a good one to look up later on. And it's related to this. You could see how it has the same pattern of calling with the address as our swap function. Okay, and second use, right? We said that C functions can only return exactly one value, and so the return value of this thing is just one name. We're just allowed to return one float. And we're not allowed to change, our variables directly. We can make them pointers. So the same way we could sort of change I and J using A and B. Over here, we can change the value perimeter in main by passing the address of perimeter, right? And so perimeter, right? It's going to hold some value. Nothing initially, right? It could be, F5, just some other address. It doesn't hold anything initially. We now get the address F5 up here, passed by value. That's our P, right? It holds F5 inside it. When we do something on this line like star P, we're following the arrow down to this memory, which is stored outside in main. We compute 2 times pi times r, which I think is the formula for perimeter, and so now we get 2 pi r stored inside perimeter, and we've modified the perimeter using by passing its address, and we modify area by returning area and then setting area equals, right? So we never have to pass the address of area. The assignment is done for that one outside in main by returning the value, and so we can actually change both the area and the perimeter. And note that r is just passed. The radius it doesn't want to change. It's used in the computations, but it's not a result. So here we can just pass it as a normal variable. We can use pass by value and all as well. And then we can print and see that and this code changes both the area and the perimeter, right? So pointers are useful. We've achieved sort of a leveling up in what we can do with our C programs, and hopefully these examples and so the box and arrow diagrams make sense to you. This is an important topic. It's not something which everyone gets very immediately, and that's okay. We're going to keep working on sort of your knowledge with pointers as 206 goes along. I recommend reading Chapter 5 in the Kernighan and Ritchie C programming language textbook, the first one in our recommended books list. It has a lot more background, and sort of go through these slides and examples yourself.